Okay, so what we're going over, sorry, Rob. Yeah. Hey, what we're going to go over today is signs of a chemical change, and we're going to go over the types of reactions. Okay, there are 5 reaction types that we're going to go over. That's probably all we'll get to today, right? But where we're headed is being able to communicate balanced chemical reactions, or chemical equations, they're sometimes called. Okay? So we'll be looking at how we're going to write those. Now, here's the thing. Being able to write a chemical reaction in either word or equation form requires you to be a master of writing names and formulas for chemical compounds. If that is something that you are still struggling to do consistently, then you need to practice it. And you need to come in and see me for some help, because it will become very difficult / impossible to write proper balanced chemical equations if you are unable to consistently write the formulas for chemical compounds correctly. Okay, so that's that fundamental skill that we have to have a mastery of moving forwards. Right? You have lots of worksheets in the worksheet booklet about naming and writing chemical formulas. Right? Make sure you check those. The keys I posted in Google Classroom a couple of weeks ago, you can check your answers as you go. If you're struggling with that, come in and see me. It's usually something simple, okay? And we can get it figured out. Right? But you have to be able to do that in order to write chemical reactions properly. Okay, what are some signs of a chemical change? Okay, so a temperature change. Triangle is delta, means change. It's a science shorthand.
Like the state of the substance has changed.
What else?
Color change?
Color change.
Like new substance is created.
Okay, those are pretty good. Those would be the basic ones. Okay, temperature change is definitely one. We will often also say energy change, because there could be different forms of energy being produced in a chemical reaction. We were just talking about the glow sticks a minute ago, this one you snap. Okay, that's a chemical reaction. The energy produced is light.
I don't know how to word it, but like an explosion of some kind. Like if there's like bubbles or fizzes. If there's a word.
Exothermic reaction.
Yeah, exothermic, that's energy change. Exothermic means to give off energy. Endothermic, like the cold packs, means to absorb. Yeah. Okay, so yes, that would be energy change. Okay, even a reaction that involves producing electric current, like would happen in a car battery or something like that, okay, that's an energy change. Electrons are flowing outwards and energy is being produced by the reaction. Okay, so it's not just temperature change. Temperature change is probably the most common one, okay, but all forms of energy, not just heat, can also change in a chemical reaction. In fact, that's kind of the reason chemical reactions occur. Matter is always trying to achieve a more stable state. Okay? Chemical reactions usually result in a lower energy and more stable state after the fact. Okay? Like for example, gasoline is quite volatile. That's why it burns so hot. But after it burns, it's a much lower energy state, carbon dioxide and water vapor. Okay? Most of the energy is being released, and we're in a lower enthalpy or entropy afterwards. Okay? That sort of making sense? Once a chemical reaction happens, in general, are they reversible?
No.
No. In general. There are exceptions. The chemical reaction that powers your phone through the lithium iron phosphate battery, okay, is reversible. Anything that can be recharged is a reversible chemical reaction. Does it reverse on its own?
No.
No. It requires an input of energy to reverse. Okay? So we technically say that no reaction is reversible, because you would have to put energy into it to get it to go back. Okay? The natural state is for it to react and then stop. All right, so yes, some are reversible provided energy is input. I can't reverse a campfire. Okay? I can't unburn firewood. Once the campfire is done, I have carbon dioxide, water vapor, and ash. I'm not getting the firewood back, okay? Campgrounds wouldn't make money, okay, if that was the case, because then you could just reverse your campfire and start all over again, right? It doesn't work that way. So most reactions are not reversible, okay? New substances are formed. That's the key, okay? That's the difference between a chemical change and a physical change, okay? Evaporating water is not a chemical change. Why not?
Because you're just changing the state of water.
Exactly. I didn't form a new substance. I still have water. It just went from a liquid to a gas. Same as freezing water. I went from a liquid to a solid. I didn't change it. It's still chemically water. It's only a physical change. Right? Even solubility, dissolving something in water, is only a physical change. I can get it back. All I have to do is evaporate off the water and I'll have back the stuff I dissolved. Right? But a chemical reaction produces new substances and is thus not reversible.
So from like the ice to water, what do you like input light or like heat to go back to water?
Yes. Okay, questions there? All right, so we're going to go over the types of chemical reactions. Like we said, learn how to identify each reaction type. The 5 reaction types are all very different. There's really no confusing them. You just have to learn the kind of format. Okay, and then obviously learning how to write them, which we will probably get to today. All right, so in a chemical reaction, this is kind of the definition of chemical reaction, so it's kind of important. Okay, in a chemical reaction, the final products are chemically different from the starting reactants. Okay, evidence of chemical reactions: color change, odor change, state change, energy change. So one that we didn't list was a gas being evolved. Okay, a precipitate being formed, okay, is another one. Usually those involve also color changes and state changes and things like that. Okay, that is an example of a properly written, balanced chemical reaction. In this reaction, I have sodium chloride reacting with lead-2 nitrate. When that happens, I get a chemical reaction that forms a yellow precipitate, because chlorine is not soluble with 2+ lead. Okay, so I would get a pale yellow precipitate being formed. Okay, that means new substances have been formed. Did I make any new elements? All the same elements. Okay, so yes, I got new substances. These new substances have different properties. This is soluble in water. This is soluble in water. This is not. This is. Okay, so I know after this reaction that I have created something different. Okay, and I know that because the properties have changed. And the only way that could happen is if I got something different than I started with. That's the indicator, okay, and why we see some of those signs of a chemical reaction. A new substance with different properties has been formed. Okay? That's why we get color changes, state changes, precipitates, gases, okay, all of that stuff being formed as a result of a chemical reaction. Okay, what's the purpose of the 2 big numbers here, the 2 2's? Yes, why? Okay. The number 1 rule of matter is that matter cannot be created, cannot be destroyed. Therefore, I need to have the same number of atoms on both sides of a chemical reaction. I can't destroy it. Something can't just disappear in a reaction. Everything has to be accounted for. So these big numbers we call coefficients. We use them to balance a reaction. That is, to ensure that a reaction has the same number and type of each element on both sides. Right? So on this side here, this 2 applies to this whole compound. So there are how many sodium atoms?
2.
2. How many chlorine atoms?
2.
Okay, if I go over here, are there still 2 sodium atoms?
Yes.
Yes. Are there still 2 chlorine atoms?
Yes.
Okay. How many lead atoms here?
1.
How many over here?
1.
Okay. How many nitrates are there?
2.
2. How many nitrates over here?
2.
2. Right? There's a 2 in front of the compound. That's the tricky part, right? Because it doesn't, we don't have the little 2 beside it. But that big 2 means everything in this compound multiplied by 2. So there's 2 sodiums, okay? That's got to be a scam. Okay. Does that make sense?
Yeah.
Okay, so everybody's good with that?
Yeah.
Okay, here's another one. Try something simple. Okay, that's a very simple reaction. Did I write it correctly?
No.
Nope. What's wrong with it?
There should be 2 bromines on the other side.
Okay, there should be 2 bromines on the other side. Does that fix my problem?
No.
No. I mean, it makes 2 bromines, but now that compound doesn't work because this is an ionic compound, and I dropped and swapped it correctly when I wrote it. This is a +1, this is a -1. So this one's okay the way I wrote it. So since I can't change the little numbers, all I can do is say, all right, I got 2 of that. But when I do that, it fixes my bromine, but what does it do to the lithium?
Makes it 2.
Is everything balanced now?
Yes.
That's how you balance a chemical reaction. Okay, you write out your products and you go, okay, I dropped and swapped them all correctly, or I obeyed the prefixes. Now I need to go back and forth and make sure that I've got the right number of everything on both sides. Okay. All right, so in both of these, was a new substance formed?
No.
Yes. Okay, so I started out with lithium, which is a soft silvery metal. I reacted it with bromine, which is kind of a brownish liquid, okay? And I got LiBr, which is a water-soluble ionic compound. It would be essentially a clear crystalline solid, okay, if it was in solid form. Okay. So we're going to go over our 5 types of reactions, starting with the simplest one. Okay? The simplest reaction type is what we call a synthesis reaction. It's like the one with lithium that we just looked at. Okay? In a synthesis reaction, 2 or more elements, usually elements, but it could be 2 compounds, react to form an ionic or molecular compound. So in any synthesis reaction, you will have 2 reactants and 1 product. So there's 2 new terms that I just used. Okay? In a reaction, this side is called the reactants because they'll react. Like that makes sense, okay? And then this side is called the products because it's what's produced. For once, chemistry made sense. So in a synthesis reaction, there are going to be 2 reactants, 2 or more reactants. It's usually 2 elements, and they're going to react and form a single compound as the product. Okay? So in this case, I had 2 magnesium atoms react with 1 molecule of oxygen to form 2 molecules of magnesium oxide.
What's the S and the G for?
Those are the states. You don't have to worry about those. I'll never ask you to write those in the reaction. But you get to Chem 20 and you'll have to start putting in the solids and the gas. And that's just a matter of looking on the periodic table at melting point, boiling points, extra stuff you don't have to do in Science 10. Okay? Magnesium is just a metal. It's a solid. Okay? Oxygen is obviously a gas. Okay? And it makes an ionic compound, which is a crystalline solid at room temperature. Right? Other example, so we've got here, okay, 2 atoms of potassium reacting with 1 molecule of bromine. How is this different? I've got 2 potassiums and 2 bromines, but they look different here. This one's got a big 2 in front of the K. This one's got a little 2 behind the Br. In the end, it still means 2 atoms of each one. But how are they different?
Bromine is diatomic, so it's bonded to itself.
Exactly. Bromine is one of our special molecular elements, or diatomic elements. Okay? It means that as an element, it doesn't come as single atoms. It comes in a molecule. All bromine atoms, but they're bonded together. Okay? In sets of 2. On your periodic table, you can pull out your periodic table. These are color-coded on your periodic table. Okay. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and aspartame are our diatomic elements. Hydrogen also, okay, are our diatomic molecular elements. When they're in their element form, that is by themselves, they are a molecule of 2. H2, Cl2, Br2, etc. Okay? Phosphorus is also a molecular element, but it comes as a quartet. That is 4 phosphorus atoms bonded together. So when you write phosphorus by itself, you write it like this, P4. Only when it's by itself. In a compound, you go with either the prefixes or the drop and swap. Okay? Only when phosphorus is by itself. These are the 4. Okay? And then there's sulfur, which comes as an octet. It is the specialist of the special elements. Okay? S8. Again, only in its element form. In a compound, you drop and swap or use the prefixes to tell how much there is. Okay? So if I had sodium sulfide, for example, okay, that's Na with S. This is a -2. This is a +1. Okay? It's still going to be Na2S. Right? That doesn't change. I don't go, oh, sulfur's always an 8. You go, okay? No. Okay? Sulfur's only an 8 when it's by itself. All right? Everybody with me? So you don't have to memorize those. It's on your periodic table. It tells you which ones are special. Okay? And in fact, on the newer periodic tables, it's also listed up top as polyatomic elements. Okay? In a small box in the top right corner. Okay? And it actually tells you it's H2, it's Cl2. Okay? It actually tells you what number goes beside. So it's listed in 2 different ways on your periodic table. Okay. Questions on synthesis reactions? Okay, so in a synthesis reaction, 2 elements combine to form a single compound. That compound could be ionic or molecular. It depends what's reacted. Right. The opposite of a synthesis reaction. Synthesis means to synthesize or put together. Decomposition means to break down or pull apart. So a decomposition reaction starts with a compound and ends with 2 or more elements. Okay? So the compound breaks down or decomposes into its constituent elements. Okay, so that's what goes on in a decomposition reaction. So this one here, okay, is kind of like what Mark Watney was doing in The Martian, if you've read the book, / seen the movie. Book's better. Movie's good. Book's better. If you get a chance to read the book. So we start out with water, and we are trying to turn it into hydrogen gas and oxygen gas, which didn't work out well for Mark Watney, if you recall. He nearly blew himself up, scorched his eyebrows, and all that good stuff. Okay? Because the byproduct of this is hydrogen gas, which is highly explosive. Okay? So it caused the Hindenburg to crash, that big Zeppelin, right? The big blimp?
Yep.
Yeah, filled with hydrogen gas. Nobody saw a problem. Hydrogen floats, it's wonderful, but it's explosive. Oh, the humanity. Yeah. All right, so that's a decomposition reaction. If I arc electricity, okay, through liquid water, I can produce hydrogen gas and oxygen gas, okay, as byproducts. That's a decomposition reaction, right? The one we see here, this is also a decomposition reaction. We've got nitrogen triiodide, and it decomposes into nitrogen gas and iodine liquid. Okay? Liquid? No, solid. Solid. Okay. Everyone follow me on that one? Now, look at all the 2s. Okay, both of these are special molecular elements. Is that something I might have to remember when I'm writing a reaction? It is. If I get this reaction in words, there's going to be no indication that nitrogen and iodine need 2's beside them. Okay, written out in words, this would say nitrogen triiodide decomposes into nitrogen and iodine. Okay, and if I'm not paying attention and I'm asked to write that out in formula form, I might go Ni3 and I'll get it wrong. That's not how that reaction looks. Nitrogen and iodine do not exist by themselves. Okay? They come as 2's. Right?
How would you know from like the written like words of it? How would you know if they like to put a 2 beside the nitrogen and iodine?
Because on my periodic table, they're listed as special elements.
No, but like for the I guess the reaction, yeah.
Oh, okay, so that's balancing. I wouldn't know this number or this number, the 2 or the 3. So when I first write this out, it would look like this. Ni3 goes to N2 plus I2. Okay, now I've made sure that I've written all the stuff that's in it correctly. Now I have to balance it. Okay, so balancing involves looking at both sides and trying to get it to work out. And so what I would do is say, okay, I got 3 iodines over here. Always start with the biggest number. Okay, and I've got 2 iodines over here. What's the lowest common multiple of 2 and 3? 6. So if I get 6 on both sides, it'll be balanced. Right? And so that's what I have to do to balance it. I kind of go with lowest common multiples. So that means put a 2 in front of this one to get 6 iodines. Put a 3 in front of this to get 6 iodines. When I do that, it gives me 2 nitrogens as well, and there's already a 2 over here. So usually when you're on the last one, it kind of works out.
Can I get the washroom?
Okay, so I wasn't actually going to, yeah, go ahead. I wasn't even going to talk about balancing today, but the question came up, so it's an opportunity. Okay, we'll go over that again later if that just went over your head. Okay, we'll do that again. All right, questions on decomposition reactions. Okay, so synthesis and decomp are the exact opposite of each other, right? And I keep kind of harping on what they look like. Okay, a synthesis reaction is 2 elements combined to form a compound. A decomposition reaction is 1 compound breaks down into 2 elements. The reason for that is, at some point, we're going to have to be able to recognize reaction types, because we're going to get to the point where we're predicting the products. Okay, you only get half of this reaction, and you have to predict the products and then write it out and balance it. That's where we're headed. Maybe not even this week, but that's where we're going. All right. So this was, I meant to show you that. So this is your periodic table. Okay, and you can see the polyatomic elements are listed up here, okay, on the very top, but they're also color-coded on the periodic table to make them pop a bit more. Okay, so you remember which ones are which. Hydrogen didn't get turned yellow on this one, but I think it is on yours. Okay, it's not great. Okay, well, it's listed over there. Okay, but hydrogen is one of the polyatomic elements. All right, combustion reactions. Combustion reactions are different. Okay? We have to treat them a little differently than other types of reactions in terms of how we balance them. Okay? So in a combustion reaction, the complete combustion of what we call a hydrocarbon. Okay? And a hydrocarbon, oddly enough, contains carbon and hydrogen. Hence, hydrocarbon. I know it should be carbon hydro, but it's hydrocarbon. Okay? Hydrocarbon combustion is what powers our society in general. Okay? It's how we make electricity for the most part. Okay? It's how we power our vehicles for the most part. Okay? It's how we cook our food, unless you have an electric stove. Okay? Or you don't use barbecue. Okay? Anytime you're burning something, that's hydrocarbon combustion. Okay? Even a campfire is hydrocarbon combustion. Now, we're talking about the complete combustion. What we're going to look at is highly simplified. In most cases, hydrocarbon combustion is not always perfect, which is why combustion can be dangerous. Not because it gets hot, but because it produces other gases, like carbon monoxide, okay, which is deadly, and we all have detectors in our homes to tell us when it's present. Okay? But we're going to look at kind of simplified ones. So in a hydrocarbon combustion reaction, we're always going to have a hydrocarbon, okay, so some C and H combination, and it usually goes in this form. It'll be CN, representing a number, and then it'll be H2N plus 2. Okay, so here's what I mean by that. Okay, in this one here, it's C is 3, but H is 8. Well, if I take 2 times 3 is 6, plus 2 is 8. Okay, that's not going to be important for you guys, but it's always going to be carbon and hydrogen together, okay, in some sort of number combination. And it's always going to be reacting with the gas necessary for things to burn. Oxygen. Okay, so if you have a reaction that starts out carbon, hydrogen plus oxygen, it's combustion. Okay? It's a hydrocarbon combustion reaction. Here's the nice thing about hydrocarbon reactions. They always have the same products. It doesn't matter what you're burning. The end products are always carbon dioxide and water. All that changes is how much carbon dioxide and water you produce. Okay, so in this reaction here, I have propane. All right, so if you have a barbecue at home, this is the reaction that goes on in the barbecue. Propane gas reacts or burns in the presence of oxygen gas to produce carbon dioxide and water. Okay. Now, most of the time, that water also comes in the form of gas. It comes as water vapor. But under extremely cold conditions, it can remain liquid. It's why on a really cold day, you can sometimes see water dripping out of the exhaust pipe of the car in front of you if you're stopped at a stoplight. Okay? The exhaust system is cold enough. Okay? The water vapor that is produced by the burning of gasoline can condense back into a liquid. All right. So this one here, is it balanced? Here's how we check that. How many carbons are here? 3. How many carbons are here? 3, right? 3 times 1 is 3. Okay? In carbon dioxide, there's 1 carbon atom. All right. How many hydrogen atoms are here? 8. Okay? How many are over here? 8. 4 times 2 is 8. All right. How many oxygens are here? 10. All right. How many on this side? Well, 3 times 2 is 6, plus 4 more is 10. Okay, this is where it can get tricky. The reaction is balanced as long as the number of each type of element is equal on both sides of the arrow. You may get an element being in both products, even if it wasn't in both reactants. Okay? And so you have to follow it all along. That's why there's a plus sign in a reaction. Okay? It's this plus that. You have to add all those numbers together to get your totals. All right, so looking at a different one, let's look at this one. Okay, so this is a hydrocarbon combustion reaction. It's the one that happens in lighters. Okay, so if you got one of those long clicker lighters, okay, stick it later. Okay. This is butane, okay, burning in the presence of oxygen to produce carbon, hydrogen, okay, carbon dioxide, and water. Now, I want to balance this reaction, right? But I can't follow the rules that we used over here. Okay? Over here I said start with the biggest number. That doesn't work in hydrocarbon reactions. So this is one of the special rules that you're going to need to write down for hydrocarbon combustion. talk much about balancing. I just want to have this on the same area of your notes as the combustion reactions. The first rule of balancing a combustion reaction, balance the reaction in alphabetical order. C, H, O. Balance oxygen last. Reason, oxygen will be in 3 places in the reaction and is thus the most difficult part to balance. It's better to have everything else balanced first. Second rule is the rule of 2. You're a Star Wars fan, you know where that comes from. Always 2 there are. But in this, it's always balanced with a 2 if there's an even number of carbons. Okay? Okay, so for example, C2H10, for it was C4H12, okay? Then as long as carbon is an even number, okay, start the reaction with a 2. That's why we call it the rule of 2. If there's an even number of carbons, start the reaction with a 2. And I'm going to show you why that is here in just a minute. Okay, so with this reaction, if I just start balancing it, I'm going to run into a problem, and I'll show you what that problem is. How many carbon on this side? 4. Okay, so I'm going to put a 4 here. All right, now my carbons are balanced. How many hydrogen here?
2.
Okay, what times 2 will give me 10?
5.
Okay, now I've got to balance my oxygens. How many oxygens here? 8. Plus 5 more is what? 13. What times 2 gives me 13? Nothing. 6.5. Can I have 6.5 oxygen molecules?
No.
No, I can't. Okay? Oxygen's diatomic. It doesn't come as a single. Having 6.5 would imply 5 whole ones or 6 whole ones and 1 oxygen atom freely. That doesn't happen. I can't have a 0.5 when I'm balancing reactions. So the only way to get rid of that 0.5 is to double it. Okay? By doubling it, I will get rid of the 0.5. So if I start with a 2, like the rule of 2 says to, now how many carbons are there? 8. Okay, so I put an 8 here. How many hydrogens are there? 20. What times 2 will give me 20? All right, now I look at my oxygens. 8 times 2 is 16, plus 10 more is 26. 13 times 2 is 26. No applause necessary. Okay? So that's why I have to use a 2 if I have an even number of carbons. That doesn't happen if I have an odd number of carbons. Okay? So if I have an odd number of carbons, let's just write one here that has an odd number. Okay, so let's say C5, H12, okay, plus O2. Oh, more space there. All right, so if I have an odd number of carbons, I don't need to put the 2 in front. 5 carbons here, 5 there. 12 hydrogens, 6 times 2 is 12. I have an even number in front of the water if I have an odd number of carbons. Okay? But if I have an even number of carbons, I get an odd number in front of the water, and then I have that decimal problem. So now if I balance my oxygens, 5 times 2 is 10, plus 6 more, okay, is 16. Whoop. Okay, 8 times 2 is 16, and I'm done. Okay, I don't need the 2 if I have an odd number of carbons. If I have an even number of carbons, I have to start with a 2 to make it balance. Okay, these rules only apply to combustion reactions. We'll go over how to balance all the other types tomorrow.